Okay, picture this, a chilly winter evening. We've got two siblings, Pema and Palden, getting all cozy by a fireplace while their grandmother is cooking nearby. It's a simple, warm scene, right? But it holds the key to a really basic question. How does heat actually move? In this explainer, we're going to follow their curiosity and uncover the three secrets of heat transfer: conduction, convection, and radiation. It all kicks off with this simple but honestly brilliant question from Pema. She's watching the thukpa cook in this big metal pan, and she wonders, why metal? Why not a wooden pan or a clay one? And that question right there, it unlocks the very first secret of how heat works. And the answer to Pema's question? Well, it has a name: conduction. This is all about heat transfer through direct contact. Or, as I like to think of it, heat by touch. So what does that really mean in plain English? Well, imagine all the tiny particles in a solid are holding hands in a long line. When you heat up one end, the first particle gets all jittery with energy and passes that vibration to its neighbor, who passes it to their neighbor, and so on, all the way down the line. The heat travels, but the particles themselves, they pretty much stay put. It's kind of like a secret being whispered from one person to the next. We can actually watch conduction happen with this classic science experiment. You take a metal strip, stick a few pins on it with wax, and then heat up one end with a candle. As that heat travels down the strip, it melts the wax and the pins start to drop off, one by one, starting with the one closest to the flame. It's a perfect visual of heat moving step by step, right through that solid material. And this little experiment reveals something super important about different materials. The ones that let heat pass through easily, like that metal strip, we call those conductors. But materials that are really bad at it, that block the heat, like wood or clay, those are insulators. And this brings us right back to Pema's kitchen. The cooking pan is metal, a conductor, to get the food hot fast. But your coffee mug is probably ceramic, an insulator to keep the heat from escaping. All right, back at the fireplace, Pema notices something else. It's not just the pan that's interesting, it's the smoke from the fire. And this observation leads us straight to our second type of heat transfer: convection. So why does smoke rise? For that matter, why does a hot air balloon float? The answer is convection. It's the rule book for how heat moves through fluids. And by fluids, I mean liquids and gases. Now, this is totally different from conduction. Remember how in conduction, the particles just kind of wiggled in place? Well, in convection, the particles themselves actually pack their bags and move. They literally carry the heat with them from one spot to another. Here's how it works. When you heat up air or water, its particles spread out. This makes it less dense or lighter. And what does lighter stuff do? It rises. As that hot, light fluid goes up, the cooler, heavier fluid from the top or sides has to sink down to take its place. Then it gets heated and rises too. This creates this amazing, continuous circular flow called a convection current. That's what's making the smoke from the fire go up. And this isn't just happening in a fireplace. It happens on a massive scale. Just think about being at the beach on a sunny day. The land heats up way faster than the water, right? So the warm air over the land rises and whoosh, cooler air from over the sea rushes in to fill the gap. That refreshing feeling? That's the sea breeze. It's just a giant convection current. And what's so cool is that at night, the whole thing flips. The land cools down faster than the water, so now the sea is the warmer spot. The air above the warm water rises, and cooler air from the land moves out to take its place. We call that a land breeze. It's a perfect, beautiful example of convection in action. Okay, so Pema and Palden are feeling the warmth of the fire. But wait a minute, they aren't touching it, so it's not conduction. And the air isn't really blowing on them in a big current, so it's not convection. This leads us to our third and final heat mystery: radiation. Seriously, think about this for a second. There's nothing solid connecting us to the sun. The vast space in between is a vacuum. It's empty. So how in the world does the sun's incredible heat get to us across 93 million miles of nothing? There has to be a way for heat to travel without needing any particles at all. And there is. It's called radiation. With radiation, heat travels as electromagnetic waves, kind of like light or radio waves. It doesn't need a solid, a liquid, or a gas to move. And here's the wild part: every single object, including you, me, and that fire, is constantly giving off or radiating heat. It's how you feel the warmth of a bonfire even when you're standing far away. Now, this principle has some super practical uses. It turns out that dark surfaces are fantastic at absorbing radiated heat, while light, shiny surfaces are great at reflecting it. This totally explains why we wear dark clothes in the winter to soak up as much of the sun's warmth as we can, and light-colored clothes in the summer to reflect that heat and stay cool. It's simple, but it's really effective science. So we've got our three main players: conduction, convection, and radiation. But here's the thing. In the real world, they almost never work alone. They're a team working together in all sorts of fascinating ways. So let's do a quick recap of the team. We have conduction, which is heat transfer by direct touch, mostly in solids. Then there's convection, which is heat moving through the flow of fluids, like liquids and gases. And finally, radiation, which is heat traveling as waves, no stuff needed at all. Each one has its own special job in the grand story of heat. Let's go back to that pot on the stove one last time. The flame heats the bottom of the metal pot, right? That's conduction. The water inside starts to swirl around in currents, heating all of it up. That's convection. And you, standing nearby feeling that lovely warmth, that's radiation. All three working together in perfect harmony just to heat a pot of water. And these same principles power our entire planet. Just look at the water cycle. Radiation from the sun heats the vast oceans. Convection causes all that warm, moist air to rise up and form clouds. It's this beautiful, gigantic engine, all driven by the simple laws of heat transfer we've just been talking about. Understanding these fundamental rules isn't just about explaining the world we see. It's about empowering us, giving us the tools to innovate and build a better future. Check this out. It's an absolutely incredible innovation from Ladakh called an ice stupa. Engineers there realize that tons of water from mountain streams just goes to waste in the winter. So using these principles, they pipe that water up and spray it into the freezing winter air. It freezes instantly, building these giant cones of ice, basically man-made glaciers. These then melt slowly in the spring, giving farmers water right when they need it most. It's genius. And that's really the big takeaway. We started with a simple question about a cooking pot, and it took us on a journey through the science that warms our homes and drives our entire planet. So the final question for all of us is this: what other problems can we solve by understanding and working with, not against, the fundamental rules of nature?